Hi friends, welcome to GMK Tutorials. సో ఇప్పటివరకు ఇంకా ఎవరైనా మన ఛానల్ సబ్స్క్రైబ్ చేసుకోకుండా ఉంటే ప్లీజ్ సబ్స్క్రైబ్ అవర్ ఛానల్ అండ్ షేర్ యువర్ ఫ్రెండ్స్ ఆల్సో. ఓకే, సో at the same time, uh, really thank to each and every person who supported me throughout the journey. So thank you guys. So let's move on to the topic. So in the last video we discussed about the some different circuits, like we can call it the CE configuration, at the same time common source configuration, and what is the necessity of a circuit is required to produce some constant current source. That the circuit may be generally called we can simply call it some biasing element point of view. Just we can call it a biasing element. Then if you want to replace the corresponding circuit with biasing elements, obviously first of all we need to study about the biasing element. Okay, so biasing element, so obviously each and every device having some characteristics. At the same time, in case of the biasing element point of view, is there any characteristics? Okay, that is a now we are going to study about that one. Okay, so now what are the characteristics of a current biasing element? So this current biasing element having a three important characteristics. So the first one is nothing but a high input impedance. Okay, first one is nothing but a high input impedance. So that means the biasing element having a high input impedance. So high input impedance means that in this case the current I can call it a current I. So this current is independent of the corresponding voltage across the corresponding element. So this current is independent of the corresponding voltage. Obviously we can get the output impedance is a very high. Second characteristics of the biasing element is nothing but a current is well defined. That means the corresponding current cannot be varying with corresponding variations. That means it is a very low variation. It is also called as the variations is also sometimes uncertainty. So that means a very small change in the current is a very negligible also. So that is also second case. That means it is negligible means the current is very constant simply, right? And third one is nothing but it operate with available supply voltage. That means the whatever the biasing element cannot draw maximum power from the supply rail. So that means obviously the power requirement for the corresponding biasing element is also very minimum. That means for a minimum voltage, with a minimum voltage, the operating biasing element should be very good. So it produces a constant current source. That is the some basic characteristics of the biasing element. So now let us see some small example. Okay, so in this case this part is generally called as a I can call this is generally called as a just a minute. This is generally called as a biasing element. This is generally called as a current biasing element. Current biasing element, simply current biasing element. So this is generally called the application circuit. So here obviously there is a current. This current is generally I can call as a I bias. So that means biasing current. So this is generally called as a voltage. That means V biasing voltage. So this is generally called as a V biasing of the corresponding biasing. So here the first point is nothing but the output impedance of the corresponding circuit is nothing but independent of the voltage across it. That means here high output impedance, the impedance of the corresponding circuit is very high. So for that purpose, let us see here, if the biasing element is independent of the V bias, that means this current is cannot independent on the circuit, obviously if you draw the characteristics with I bias and V bias, so I bias does not changes with the V bias, it maintains some constant value, right? So if you are taking a constant value means that obviously the slope of the corresponding line is also 0. Okay, if the slope of the line is 0 is nothing but we don't have any resistance, so there is no resistance value is also, output resistance is infinity. Output resistance is infinity. So that means there is a changes in the VBS. Suppose if you are taking like this, so this is nothing but a VBS. So VBS, some value at the same time, so change in the current is equal 0 only. So if you are taking a change in current is equal 0 only. Therefore, obviously that leads to infinity. That means the corresponding output resistance value is a infinity. That is the main thing, right? Now, second thing is nothing but so same characteristics point of second analysis is nothing but so I bias is also not changed by the application circuit voltage. So there is maybe cases here also. So there is some cases it is also having there is some voltage. This voltage is produced due to the application circuit. At the same time here also same thing, the biasing current is also not it also not depends on this voltage also. So irrespective of this voltage or my biasing voltage of the corresponding circuit which produces a constant current source. That is a very important. That is nothing but second rule. Okay. The same way, those are the three important considerations. So now let us see the what are the different versions in case of the biasing element point of view. So the current biasing elements to current mirror. So how it is leading to the current biasing elements leads to current mirror circuits. So what is the journey of this one? What is the journey behind the current mirror circuit, or what is the evolution of the current mirror, where it is started first of all. So for that purpose, let us see, we can take different situations. Suppose if you are taking the current biasing element, the biasing element, if you are choosing the biasing element is some kind of a resistance value, if you are taking some resistance value, if you are taking some resistance R value, so here the problem is nothing but if the R value is increases, okay, if your R value is increases, the gain of the circuit increases. But the problem is that nothing but this output resistance, okay, the output resistance value is decided by itself only. At the same time, the voltage drop across the corresponding is also, the voltage drop across is also increase, voltage drop is also less across it, but output impedance is high input. So that means in case of the characteristics of the biasing element, current biasing element, the first criteria is nothing but high output impedance. If you are maintaining the resistance value is very high, obviously the drop is also increases. Drop is also increases. So that does not satisfy the first criteria. Suppose if you are not increasing the resistance value to the maximum value, obviously that means that the voltage gain is also decreases. That is a problem with this one. Okay. So that is a limitation of the first case. So at the same time, in this case also, second that is nothing but here the biasing is provided by the VGS, RBB, VG, VBE. So the first case is nothing but first case problem is nothing but resistor itself only decides the output resistance. So for that purpose, instead of this resistor, I will take one more circuit analysis. The circuit is nothing but generally we can call as we can take with the help of a transistor point of view and with the help of a MOSFET point of view. In case of the transistor point of view, just we will take some biasing voltage. At the same time, it is nothing but CE configuration. It is nothing but a MOSFET with the CS configuration. So in this case, the biasing element is also need to provide biasing voltage is also provide to the transistor in order to operate the transistor in the linear region or maybe active region. So in an active region only, the corresponding circuit maintains some slope. At that time, there may be a possibility of the first criteria. If whenever the slope is there, at that time there is a possibility of resistance is also there. If the resistance is there, obviously we will check whether the resistance is a high or resistance or low resistance. The first condition for biasing element is nothing but high output impedance. That is the first criteria. Okay, so that is the case here also. So is there any drawback in this case? Means that obviously there is some drawback. So these MOSFET and bipolar junction transistors also provided with some biasing elements. That biasing element is generally called as a maybe VGS or maybe VB. So in case whenever the circuit is in operating in the active condition, then only it is useful for this one. But the problem is that if you are using the corresponding transistor in a active region, obviously that can be possible with the help of some operating point. That is also we can call as a Q point. The selection of the Q point is also decided by the biasing voltage, right? The biasing voltage is nothing but maybe VCE. Biasing voltage is nothing but like VB in case of the transistor point of view, VGS in case of the MOSFET point of view. But these voltages also may be varying with the temperature. Okay, varying with the temperature or maybe small changes in the supply voltage. There is a possibility of variations in the corresponding output also. That is a drawback in case of this one. But let us see some circuits. Application circuit decides the VC and the VDS values. So the current flow, the corresponding active region is also limited by the IC is equal to VCS. The drain current is also low independent on VDS. Here also the output or the slope of this one is equal to some constant. Therefore output resistance is also infinity. Okay, so infinity. So here the problem is nothing but variations of the temperature, the IC and IDS values also changes. That is a drawback. So for that purpose, okay, just I will take one more circuit, the circuit which is having some resistance value. Instead of directly replacing the corresponding circuit, just I provided some biasing with the biasing element like RD and IB point of view. In this case, if you are taking in case of the transistor point of view, maybe RD, if you are taking a like just RB point of view, just if you are taking a RB base RB point of view, take this collector current. So here the bubble represents, the bubble is connected to the application network. The bubble is connected to the application circuit. Here also, this bubble is used to connected to the application circuit. Connected to the application circuit. So here the problem is that if you are is there any changes in the IB value? Obviously IC value is also changes. That means here there is no possibility to get a constant current. Why? Because this base current is also varying, or maybe beta of the transistor is varying. Obviously the corresponding current is also varying. That is one problem. At the same time, if you go for the field effect transistor, why we are choosing this IB and all those things? It is necessary to operate the device in an active condition. At the same time, in case of the MOSFET point of view also, so we are using some voltage divided network current R1 R2. Is there any variations in the resistance values and biasing of the corresponding device? Obviously there is a changes in the signal, changes in the current also. At the same time, suppose in case of if you are taking a MOSFET point of view, there is some equations related to MOSFET, that is nothing but IDS is equal to K dash L by K dash by 2 into W by L into VGS minus VTH whole square into 1 minus lambda. So here, so in case of the MOSFET, the current is also decided by the parameters. That parameters is generally called process parameters. Okay, that means the length and W by L ratio is also decides the output in case of the corresponding MOSFET also. That means the IDS is also depends on the different factors in terms of VGS, VTH. That's why here also we are not getting a constant current source without depending on the without depending on the process parameters, temperature variations, and supply voltages also. So there is we need a more circuitry to produce a constant current, right? So So this is a finally last generation. We can also discuss a fourth generation. Okay, we can finally call it a fourth generation. Up to now, just we discussed three types. This is also one generation. This is a second generation, and the third one is nothing but this one. This is a third generation. So this is a, I can call this a third generation simply. Okay. So there is a one more network that is nothing but a fourth generation. This circuit is generally called a current mirror circuit. Okay. The circuit is generally called a current mirror circuit. In this current mirror circuit, so what is the thing is that just we will take a two transistors M1 and M2. So this is nothing but MOSFET, right? Metal oxide MOSFET, metal oxide semiconductor field effect transistor point of view, right? So here the thing is that this is an application circuit. This is generally called as application circuit. So this is a I reference value. So this current can be treated as a I1. This current can be treated as a I2. Right? This current can be treated as a I2. So this device can be treated as a M1. This device can be treated as a M2. So this is a mechanism we can design a circuit. The circuit produces a constant current I2. Okay. So here, let us see here. Due to the I1, there is some voltage drop. This voltage is generally called as VGS. Okay, due to the parameter variations of the corresponding W by L ratio, at the same time based on the reference current as well as supply voltage, which produces some voltage here. This is generally called as VGS1, right? This is generally called as a VGS1. At the same time, for a second transistor VGS2, this voltage is also dependency on a VGS as well as a corresponding threshold voltage. Why? Because this MOS transistor, MOSFET is also depends on the VTH voltage. VTH is nothing but a temperature variation. VTH is nothing but threshold voltage. Okay, this VTH is not the threshold voltage. This threshold voltage is also depends on another parameters, like in terms of physical parameters, okay, or maybe related to the size dimensions of the devices also. So that is also very important thing. At the same time, suppose if you are taking this one, this point of your VGS1, that means the VGS2. This VGS2 is directly depends on VGS1. Why? Because if the VGS2 is nothing but VGS2 minus VTH, this is a generalized formula. Suppose if you are taking a VGS1 is equal to VD plus VGS, VGS plus VTH minus VTH, these two get cancelled, you will get only VGS. So there is a variation in the VGS1 is also does not depends on the process parameters, then only we can get the output of the corresponding circuit. So this is all about the journey of current mirror circuit. So where current mirror circuits and what is the problem with current mirror circuit? Okay, so that means the journey starts from somewhere else. Like if you are taking a small resistor from resistor to second stage, and in case of the resistor, the complete value can be decided itself only. That is also one of the drawbacks. So in the second stage, we will take like a transistor and MOSFET point of view. Just these transistor and MOSFETs also depends on the biasing of the nature of the devices. So biasing elements also depends on temperature variations and supply voltage. So there is some more circuits also required to produce a constant. In the third case, we will take some biasing of a resistance. So here also same thing. If the resistance also having a different variations, obviously the collector current is also affected. So likewise in case of the MOSFET also, it also depends on different parameters, like in terms of the process parameters as well as the temperature variations and all those things. Okay. So this is all about how the journey started of the current mirror circuit. This current mirror circuit does not depend on any another parameter variations. So that's why the current mirror circuit is the best circuit to produce a constant current source. So in the next class, with the help of a current mirror circuit, how can we generate a CE configuration? Suppose if you are taking the CE configuration, how can you design CE configuration with the help of a current mirror circuit? Okay. So thank you for watching GMP tutorials. Thank you.